Welcome to this explainer by Forge College. Today, we're tackling interoperability and architecture impact on Solana Throughput. We're literally laying out the engineering blueprint, orange ink on beige paper and all, to understand how FireDancer's unbelievable processing speed interacts with the broader Solana network. We're moving out of our isolated, perfect little testing environment and looking at what actually happens when our hyper-optimized code meets the wild realities of a global, decentralized cluster. Okay, let's dive right into this. If you recall our last lesson, performance optimization strategies for FireDancer, we were obsessing over micro-optimizations, right? Reducing latency, grouping signature verification, shaving off CPU overhead. It was basically like tuning a high-performance sports car in a private garage. But this lesson, we're looking at macro-level cluster interoperability. We're taking that perfectly tuned, absurdly fast sports car and merging it onto the public highway, which, as you know, is filled with standard everyday traffic. To navigate this, we've got 5 specific schematics on our blueprint today. First, the node versus the network. Second, unrolling the FireDancer blueprint. Third, hitting the protocol boundaries. Fourth, estimating your node's throughput. And finally, achieving total network harmony. Let's get to it. Section 1, the node versus the network. So, let's introduce the core conflict here. What exactly happens when our hyper-optimized FireDancer node, which is processing massive amounts of data in parallel, actually has to communicate with standard Solana validators out in the wild? Well, it leads us to a pretty funny kind of counterintuitive question. Can being too fast actually break the network? No way, right? But think about it. Imagine you're invited to a casual dinner party that starts at 7 p.m. You decide to be incredibly efficient, so you show up at 4 p.m., stand aggressively at the front door, and demand appetizers. The host isn't ready, the food isn't cooked, and your so-called efficiency just caused a massive logistical headache. That's exactly what a highly optimized node can feel like to the rest of a standard network. In systems engineering, we actually have a term for this: interoperability friction. It's the performance degradation that happens when an ultra-fast node's batching meets standard validators that are expecting, well, a much different timing profile. Massive intranode concurrency can accidentally create major traffic jams in internode communication. Basically, the blistering speed inside your node doesn't neatly map to the communication patterns outside of it. Part 2, unrolling the FireDancer blueprint. To understand exactly where this friction originates, we need to look under the hood. If we trace the code-level path of a transaction across our engineering blueprint here, it looks something like this. First, the receive loop gathers incoming packets over UDP. Second, they're grouped into a packet batch. Third, the signature worker kicks in, utilizing data parallel verification across a thread pool. And fourth, the XX stage applies those transactions sequentially to maintain determinism. Now, batching at the ingress level here is great because it dramatically reduces CPU overhead and system calls, but it inherently increases queuing. So the crucial point here is that every single code-level batching choice you make directly impacts your measurable throughput under heavy load. Batching is all about grouping operations to amortize that per-batch overhead. You're deliberately trading a slight delay, what we call per-transaction latency, for a massive, massive boost in maximum throughput. It's a calculated trade-off, for sure. Section 3, hitting the protocol boundaries. But here's where things get a bit tricky. We have to shift our focus to the actual Solana protocol touchpoints. This is where our fast, isolated FireDancer node bumps into rigid network-wide rules. And the most famous of these? Proof of history, or POE. Think of the POE cryptographic clock as a series of rigid traffic lights, establishing ordering windows via leader ticks. If our internal node's massive batches end up delaying packet forwarding beyond these expected ticks, well, we miss the green light. The result? We force the leader to produce blocks with uneven transaction density, which actually degrades the end-to-end cluster throughput. There are actually 5 critical interaction stages where FireDancer's internal design rubs up against standard external network boundaries. First, as we just mentioned, network ingress interacting with POE ticks. Then we have batching, creating asynchrony in signature verification. From there, execution runs right into account locking and contention. Next up is transaction propagation, hitting gossip rate limits. And finally, writing data hits the storage commit limits of Cloudbreak. Let's look at dispatch policies using a factory conveyor belt analogy. Eager dispatch is basically like throwing everything onto the belt as fast as humanly possible. Sure, you get absolute peak transactions per second, but you risk priority inversion and literally dropping items off the side. Pace dispatch, on the other hand, carefully spaces out the items.
It preserves ordering and creates interoperability harmony, even if it costs you just a tiny bit of peak throughput upfront.
We also really have to consider gossip. That's the protocol for propagating transactions and votes across the network. If your node batches too aggressively, it generates incredibly loud, dense bursts of messages. And this can completely overwhelm peer nodes that have smaller, more conservative receive buffers. They literally can't handle the noise. So what do? They drop the packets. Yeah, your node's incredible speed actually causes data loss on the network. And let's not forget Cloudbreak, Solana's storage backend. Writing ledger segments is heavily I/O bound. Now, if you group writes into larger segments, you definitely improve your input-output efficiency. But this increases commit latency and stretches out the recovery window. Stalling here with massive batches can severely impact leader rotation and fork choice, which is obviously not what we want. Section 4. Estimating your node's throughput. Understanding these boundaries is essential, but how do we actually test them? Well, we always emphasize a hands-on approach. Let's introduce a simple Python script approach to estimating your local TPS before you ever go live and disrupt the network. Now, what's really interesting about this slide is how tuning specific variables or knobs changes the entire TPS equation. For example, increasing batch size amortizes your overhead for higher sustained TPS, but it risks tail latency. Expanding the worker pool improves parallel validation, but only until you hit CPU saturation. And I/O coalescing reduces system calls, but as we saw, increases that storage commit latency. Let's say you decide to just crank the worker pool up to 8 workers, or even higher. It's absolutely crucial to remember that scaling TPS with workers has diminishing returns. If you aggressively add more workers than you have available hardware cores, your node doesn't magically get faster. Instead, it gets bogged down with context switch overhead. Your workers basically start tripping over each other. The takeaway here is that chasing pure peak TPS on a local machine almost always comes at a hidden cost: tail latency. This is the delayed response time for the slowest transactions in your batch. When load spikes, or during leader schedule changes, high tail latency on your ultra-fast node can cause massive timing friction for all the broader network peers that are just sitting there waiting on you. Section 5. Achieving total network harmony. This brings us to our final, and honestly, most important point. We need to define the ultimate architectural goal, which is carefully balancing your single-node TPS with the hard, undeniable realities of the global cluster. To summarize our blueprint, we have 3 concrete principles of FireDancer architecture. First, batching and parallelism are powerful multipliers, but they always trade off latency and timing granularity. Second, protocol boundary points, like POH ticks and gossip limits, act as hard, inflexible limits. And third, effective tuning requires a strict analytical testing workflow. Batching is a careful tuning parameter, folks, not a magic bullet you can just crank to maximum. And this brilliantly illustrates how top-tier developers actually work in practice. You must map cause to effect using controlled parameter sweeps before you even think about a large-scale deployment. You form a hypothesis linking a code-level knob to a TPS change. You run the sweep, and then, crucially, you measure both the node-level and cluster-level metrics, like packet drop rates and commit latency. Our source material provides a perfect guiding rule here. Changes that alter external timing must be validated against a representative set of peers. Optimizations that stay entirely internal to your node, those are completely safe. But any optimization that causes external burstiness has to be carefully managed. Otherwise, you literally run the risk of reducing the effective throughput of the entire cluster. All right, you should now be able to prepare synthesis notes linking your FireDancer tuning knobs to expected throughput changes. And this perfectly sets us up for our next lesson in the module, Data Management Fundamentals in FireDancer. We're going to take these synthesis notes and map storage and ledger strategies directly to recovery trade-offs. So I'll leave you with this provocative question to ponder. Are you tuning your validator just to show off peak bench numbers in a vacuum, or are you actually engineering for true network harmony? Thank you so much for watching this explainer. To continue exploring our content and mastering Web3 concepts like this, please visit forge.college. Keep building, and I will see you in the next one.